Okay, hi. So now that we know how to estimate G, gamma by G, by our Gauss-Newton method, we can talk about making inferences on gamma. So here's the model again, just to refresh your memory. Yi equals some function of the predictors and the parameter vector gamma plus an additive independent normal 0 sigma squared term. Just like in linear regression, this is not any different. The difference is this function is nonlinear. So for notation purposes, from the Gauss-Newton method, we're going to let we'll write G with no superscript, and this just means the approximated least squares estimate for gamma from Gauss-Newton. And we'll let y hat be f final. That is really the final fitted value. This is just f evaluated at now the final parameter, right? And that's what you just put in your final parameters. That's your best shot at gamma. So you plug those in. Leave x a variable, and that should give you your fitted value, your function. Or if you want to talk about, y hat, then y hat I, if you want this, we could do that, right? So that gives you your final fitted value. Also, we'll just let D equal D final, and this will just be the matrix of partials. So this is matrix of partial derivatives evaluated at G, the final, okay? Matrix of partials eval at G. Okay, so we have this theorem. As you might have guessed, G is not normally distributed, but we do have a theorem that says when n is sufficiently large, you get some large sample theory stuff kicking in, central limit stuff, and G is approximately normal. G is approximately normal, it's approximately unbiased, and we can specify its variance by this expression. Okay, so yep. Okay, so where D is that final matrix of the partial derivatives. Okay, so this would be the estimated variance, right? Where sigma squared is replaced by MSE. What's MSE? MSE is the same as before. It's the sum of squared errors divided by n minus p. Okay, so first question, what does n sufficiently large mean? There's no particular rule or cutoff value. Wouldn't that be nice? Nope, not one. However, in the example in the book, n was only 15, and it was remarkably fast and adhered to some other tests, which showed that it was acting very normal, even for n equals 15. General, you might think bigger than that, but there's no really rule anyway. So some markers that it is normal is if you get a fast convergence of the Gauss-Newton. If I said Markov, I should have said Newton. There is the Gauss-Markov theorem, but fast convergence of Gauss-Newton method, GNM, that implies normal G. Okay, if it converges quickly. And another thing you can do is test using bootstrap methods. Okay, so this involves taking your original data and resampling it and looking at subsamples and resampled data and computing G again for different samples of from the original data. So this is a resampling method. I'll talk about it. It's not complicated really. How to do it anyway. So with this bootstrap method, we can check normality, see if normality is reasonable. We can check expected value of G, see if it's reasonably unbiased, variance of G, and from this stuff, we can, even without this, we can also estimate confidence intervals. Okay, so this can be very useful because what we'll do is we'll use the theorem here and assume normality usually, and then this will allow me to, you can see probably already, make test statistics and things that are either normal or T or F distributed. So we'll have that approach, and then we'll back it up with the bootstrap methods. That would be the way to do it probably, not to rely on just one or the other. All right, well, what are some of the tests then? Well, if G is normally approximately, and we'll talk about the bootstrap below, but let's assume for now we will assume it is and proceed with some tests and get some results, and then use the bootstrap to check that as a backup or something. Well, if we can say E, say of GK is approximately gamma K, and then this is our expression for the estimated variance of GK. Here I wrote, it's this, right? But it's the K plus first diagonal element of this, right? It would be S squared of GK. The reason it's K plus 1 is because the first element here is actually S squared G0, right? So you get, this matrix actually looks like S squared G0, dot, 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 and down here you have S squared G P minus 1. And then you have your covariance, estimated covariances over there, or your, yep. Okay, so, so we have this. If we have this, if we can assume normality and everything, then I can make a T random variable here. Remember, this is unknown, but this is random. So if the expected value of GK is gamma K, then I can subtract it. GK is normal, so I've created a T statistic here, a T distributed random variable. So this is T n minus P. P degrees of freedom are lost in estimating the P parameters. And so a 1 minus alpha confidence interval for gamma K then is, you should be very familiar, this is just repeat of the stuff from linear regression. Also, I can do a test, H0 gamma K, say equal to some value here, gamma K null, say, versus HA gamma K not equal to gamma K null. And again, I get the same t-test statistic. Rather, this is T distributed under H0, right? When gamma K actually equals gamma K 0. Then this is T n minus P. And I can do an alpha level test if I make the rejection region only reject if the absolute value of T star is greater than T n minus P. Okay, well, we could do other tests too. Well, I could do, for example, I could do an F test on a full versus a reduced model. So we could also test several variables that way, testing several variables. Several significant parameters, say. And this would be what you would expect. We would just use the general linear test approach. So say I have yi equals 0 plus gamma 1 plus gamma 2 exp xi2 say gamma 3 here plus epsilon I, and say the reduced model is yi equal, let's just make it easy, like xi1 plus. something like this, if I want to test the significance of this constant term here. Maybe I don't need it. Well, something like this I could do by just fitting, so you fit F, and that gives you, that leads to SSE F. Fit R, that leads to SSE R. And then let F star equal SSER minus SSEF over DF R minus DF F. In this case, it would be 1 divided by SSEF over DFF. And this is F distributed with 1 in this example. And this would be n minus 1, 2, 3, 4. So n minus 4. Okay. All right. And you can look up other examples too on this. All right. So we'll stop now, and we'll talk about how to use Bootstrap to support the results from these tests about the distributions of the parameters. Okay, and then you can use it for other things too. So that would be the next lecture. Okay, and this is going to be about do it. So we'll have the lecture on Bootstrap, and then maybe an R demo with some real data or something like that. But that's about it. Okay, thanks.